So hi guys, so from today we would be starting off with a new series that is reviewing some machine learning and deep learning research papers by famous personalities, and in this we are going to study about the whole research paper, what all is written in it, what you can learn from it, and how the things written in it can be useful to you. And I will also link the the research paper in the description section. So it would be like a big video, maybe around 20 minutes or to 30 minutes long video, but yeah, it would be totally worth it. So it would be around one video of a research paper in a week, because it takes time for me to read about the research paper and get some knowledge and prepare some material for you. As you can see here, I have did. So starting up with the research paper, this is the first research paper that I have got. It's a research paper that by Pedro Domingos. If you want to know more about him, all the credits are to him for this video. Yeah, he's yeah, you can see he's a professor emeritus for computer science and engineering at the University of Washington. So yeah, he's an awesome guy, and he has done the master algorithm, how the quest for ultimate learning and all. He's written a lot of things related to deep learning, machine learning, artificial intelligence, data science, and yeah. So I'm just using one of the research paper of him. This research paper is named "A Few Things Useful to Know About Machine Learning," tapping into the folk knowledge needed to advance machine learning applications. And what are all things we are going to learn here? It's written machine learning algorithms can figure out how perform important tasks by generalizing from examples. This is often feasible and cost effective where manual programming is not. As more data becomes available, more ambitious problems can be tackled. Machine learning is widely used in computer science and other fields. However, developing successful machine learning applications requires a substantial amount of black art that is difficult to find in textbooks. The article summarizes 12 key lessons that machine learning researchers and practitioners have learned. These include pitfalls to avoid, important issues to focus on, and answer to common questions. So yeah, basically before starting off, I would just give you a brief into all the overview of machine learning, how things go on. So machine learning is like, you can imagine like this is a ball, that is machine learning. Rather I would use a big ball here. So yeah, I would just use this ball, which is machine learning. Okay, this is also not a good one. I would just use some, yeah. So you can imagine machine learning as this ball, and after that you can imagine artificial intelligence to be the surrounding of the ball, and after this inside it, it would be like this is the small ball, that is deep learning. So artificial intelligence is the field that surrounds machine learning, and inside machine learning there is a ball that is for, yeah, that is for deep learning. And this is how all the things follow on in machine learning. All the things go inside each other and perform tasks that are assigned to it. And that this inside part, that is deep learning, is, I guess, the most important one and most used tasks. For the series I have created on TensorFlow, deep learning is the major part that is being used in the series overall. And this is how all the things work on. The whole graph works like that. That is artificial intelligence, then machine learning, and then inside it deep learning. So this is how the whole graphs work on. And while we study about machine learning, one thing that I want to show you all is that whenever we start preparing a model, there are some essential steps that have to be followed. That is preparation of data, because data is a thing that is used in every machine learning model. If you have seen my TensorFlow series till now, you must have got an idea that if we want to use artificial intelligence or machine learning, data is the most important thing that has to be used, because inside data there are a lot of things present. For example, data provides us what our model to do, what to do, and then it also provides us how to do. Suppose, yeah, how to do, and it also tells us the model what to do. Yeah, so this is how the whole patterns work like. So our first step is to prepare the data. Our first step is to prepare the data. And once we are done with data, what we do, we split our data. We split our data into two parts. And splitting the data into two parts is like splitting it into training, that is training, and then testing. There are two types of data, training and testing. So these are the part on where this is the part at which our whole algorithm plays around each other. We give our model this data, this particular training data, to learn on and just see how all the things are going on and just learn. For example, when there is a small baby in your house, you must have seen parents telling it that learning specific things like this is a chair, this is a table, and just like that in models the training data comes into play after you have defined the data to it, that this is the particular images, set of images, or computer vision or natural learning processing to learn things. And after that comes the testing data. The testing data works like that after you have defined the training data to your model, you test it on specific features. This is the evaluation part, that how your data is performing on the training data. So once you have done with your training data, you test your model on this particular data. It usually works like that you give almost 80% of your data for training and around 20 to 15% of your data for testing, that seeing how your model performs. But yeah, this is totally dependent on how productive your model is. You can even give it more data, and after that your model is ready to get deployed. We are not going to talk about production part or deployment part right now, but rather on all these three things, that is data, because data is the most important thing in machine learning and deep learning. So once we are done with this, we come to the next part of research paper, that is learning. So here you can see learning is equals to representation plus evaluation plus optimization. Suppose you have an application that you think machine learning might be good for. The first problem facing you is the bewildering variety of learning algorithms available. Which one to use? There are literally thousands available and hundreds more are published each year. The key is not to get lost in this use space, is to realize that it consists of combination of just three components. The three components are, so this is the main part we are going to talk about: representation, evaluation, and optimization. So whenever we talk about a machine learning algorithm, we don't have to learn a particular algorithm. Suppose you have around four algorithms available, that is A, B, C, and D. Now you have to choose between all the four algorithms, that which algorithm you have to use. At this point, you have to determine which algorithm is best for your model depending on the type of data and production and evaluation you want. Suppose A algorithm is not performing good, it doesn't mean you have to keep relying on A algorithm because A has been part of your previous all models. It can be C or it can be D depending on what you expect from the model, not from what previous results were. So this is how you evaluate. The 3 points are as told by in this research paper, that is representation. The first one is representation, and the second one is evaluation, and the third one is optimization. Now let's study about these in detail. Coming to the part that is written in this research paper, a classifier must be represented in some formal language that the computer can handle. Conversely, choosing a representation for a learner is tantamount to choosing the set of classifiers that it can possibly learn. This set is called hypothesis space of the learner. If a classifier is not in the hypothesis question space, it cannot be learned. A related question is that I can address later is how representation the input, in other words what feature to use. So the main important line is this: can be represented in some formal language that a computer can handle. Conversely, choosing a representation for a learner, that is choosing the set of classifier that it can possibly learn. You have a lot of classifiers in your machine learning model. Suppose there are six classifiers. Now depending on that, all things come up to the play. It's, you can suppose that whole model as representation part, connecting to evaluation, then optimization. But focusing on a single thing might help you, because maybe you want to focus on the classifiers or features you have provided to your model. Now comes to the second part, evaluation. An evaluation function uh, is needed to distinguish good classifiers from bad classifier. Now suppose I would come to a conclusion here that suppose, just like previous example, you have three models, that is A, B, C, and here is your data. You say, okay, I will provide data to A, to B, to C. I have provided my data to all the three algorithms, and after that I have done my compilation and all, and now I want to see which model is performing best for me. How would you do that? With the help of evaluation. Every deep learning network that is working inside the convolutional neural networks is going to work like that. You cannot be on a single set of algorithm. You have to keep testing algorithms, because it depends totally on what you want from algorithm and what data you are giving to it. Now suppose A is giving me an accuracy of 79%, let that be 79, and B is giving me an accuracy of 81. C is giving me an accuracy of around 93. Now which algorithm to choose here? That is obviously C, because it's giving me the best accuracy. But it's totally possible that if you give it another set of data and you are expecting something other from the model, maybe A would give you 97, and yeah, A would give you 97 and C would give you only 36. It's totally possible. So it totally depends on how your data is giving you evaluation after you have done with the algorithm. So is the evaluation function used internally by the algorithm may differ from the external one that we want the classifier to optimize for ease of optimization due to the loss issues I will discuss, obviously the research paper one. And finally, we need a method to search among the classifiers in the language for the highest scoring one. The choice of optimization technique is to efficiency of the learner. I have told you about the optimization function in the Kera's video also, that optimization is a very big thing that comes into play. I would suggest you to watch that video and learn how optimization and optimizers and all things work. So yeah, these are the three things that matter in choosing an algorithm. Now coming to the part, it's the generalization that costs. It's a really big thing, because the next two pages are all over about generalization. The fundamental goal of machine learning is to generalize beyond examples in the training. So I won't read every line now, but I would directly jump to the conclusion what this two pages are trying to say. Now suppose I have a model here and this is the graph. Okay, I would just erase it. Yeah, and this is a graph of the model. Now suppose this is the training set here. Now on training set, this is the accuracy. My training set is performing pretty well. It reaches around like 95 accuracy. But coming on the testing set, my model reaches only around 61. Don't you think this is a very huge difference here? And there are chances, even sometimes, that suppose you have tested your data and it's reaching around 99 here, and your testing data is only giving you 32. There are chances even just like that, because I have worked with TensorFlow and sometimes some models perform like this. So this case is called overfitting. This whole case is called overfitting, that your model is not basically learning from what you have given to the data. It's just gasping up, not understanding what to do from the data. It's learning. Suppose I would just show you a picture here. Yeah, suppose you have a model. I would just choose a pen here. Yeah, yeah. Suppose you have a model here and you have given it a set of dogs images. Now if suppose you have given it images around like 30 around 300 images. Okay, you have given it 300 images of the dog, and after the evaluation you see that your model is only able to classify dogs like this, not the black dogs. Now what is the reason here? It's known as overfitting. It's clearly overfitting. The reason for overfitting is because your model is not able to recognize that, okay, these are the features I have to learn, but rather it's learning from the images you have given to it. Instead of looking at the features like like the eyes, nose, tongue, or any other feature of the dog tails and all, it's rather learning the image. It's like gasping up that, okay, these are the images of dog, and if something like similar like this appears, I would only respond to it. This is where variety of data matters a lot. This is the fairness where it all matters. So I would just show you the fairness. To avoid that, before avoiding that, yeah, let's look at this graph. Now suppose you are working on a model, and in your model you have got two. I would just choose the similar pen here. Yeah, suppose you have this line, the black line, and you have got another line that is, let that be red. That line is like something like this, yeah. The Now which model would you like to choose? Because here you can see what the model is doing. These are the blue features and the rest are the red features. Now the model is doing what? It is just gasping up that okay, these are blue features, I'm going to predict this, predict this, predict this, these are red, these are blue. It's doing something like that. It's not a variety of data it's working on, it's not the features it's working on. Rather than, if you see the yellow line here, that is the black line in the image, it's totally consistent throughout the model, and it's not varying anywhere. It's just similar and performing at the evaluation part. Now this is how our whole process is going to work. We are going to look at the images and just predict, not directly predict, but we have to make the model learn the features that are in the images. For that, let's go here and look at what kind of examples we can take in our daily life. Suppose there is a company named X, and it's designing algorithm to make the model learn that okay, this is stone, paper and scissor. Now what happens if company only gives it images of white people, only white people? It gives images to the model only of white people, of white hands, of stone, paper and scissor. At that point, if we give a model some images of people who have got some other color, that is, let that be brown or let that be black, at that time what would happen? The model would lose the variation. It would simply give that okay, these are not part of anything, because simply how the model would be able to learn. This is known as fairness and diversity of the model. We don't want a model to perform like that. We don't want a model to perform in a unvariative way, because this is how machine learning looks like. We want a model to be fair for everyone. We want a model to be fair for all the communities and all the things it's looking at, not only humans but all the other things. This is known as overfitting. This is one of the example that I gave you of overfitting, that the model starts gasping up and learning the images based on the color or on the irrelevant features that it should learn on. It should rather learn images on the basis of features like eyes, nose, four legs, something like that. So here you can see, when it comes to the fun yeah, notice that if there are 1,000 words in a dictionary, the spam filter described has 2 raised to the power 1,000 stable inputs. Doing well on training set is easy. Just memorize the example. The most common mistake among the machine learning beginners is to test on the training set data and have the illusion of success, because it's obvious. Just imagine I give you some data that is 1,000 alphabets. Now at this point, it's really easy for you to just learn all these alphabets and perform. Okay, like okay Vishesh, you have given me this data that is a particular X data. I would simply give X because I have already learned that in the training set. But what would happen if I give you something out of box? I give you, okay, my model, I am giving you a data that is Y. Let that be Y. Now how would you perform on Y? If it doesn't perform on Y, just remember your model is learning, it's not learning. It's just gasping up thick, it's not learning from the features of the data that are available. So memorizing is a different thing and learning is a totally different thing. You memorize something is like you are just knowing that okay, this is something I was told and this is something I would respond. But learning is something that you learn from the features of the data, like from the images of the dog. You can expect like something. I would just choose, yeah, you choose something from eyes, you choose something from four legs, you tail and nose, eyes, yeah, something like that. But if you are just on the basis of colors, that is totally irrelevant feature, because there are a variety of dogs that are of different color that you haven't shown in the image. So this is how all the things here in machine learning and deep learning works, the set of whole convolutional neural networks. Because model works something like this. This is the DL, and this is how the result would come. These are the three features, and it would something look like this. Now this and this and this, and after evaluating this, this is the whole machine, the convolutional neural network would look like. So yeah, so this is how all the generalization in data counts. Generalization begins the goal that has another major consequence is that data alone is not enough. No matter how much you have it, consider learning a Boolean function of say 100 variables from a 2 million examples. There are 2 raised to the power 100 minus 10 raised to the power 6 examples whose classes you do not know. How do you figure out what those classes are? In the absence of further information, there is just no way to do this that beats flipping a coin. This observation was first made by philosopher David Hume over 200 years ago, but even today, many mistakes in machine learning stem from failing to appreciate it. So overfitting, yeah, this is, you must have got an idea if you learn this in deep, that like smoothness have similar examples, have similar classes. There are a lot of classes available in a machine learning model. This is means you can imagine like that if you have a data based on census. Now in that you will find around 300 to 400 classes. If you ignore a single class because of the data is in present in it you don't like, just expect the input to be the output to be same, because if you remove a single class, there are a lot number of features that are getting removed from it. So overfitting has many phases. What if the knowledge and data we are having is not sufficient completely determine the correct classifier? Then we risk of just hallucinating a classifier that is not grounded in reality and is simply encoding random query quirks in the data. The problem is called overfitting and is the bugbear of machine learning. Yeah, this is the example I was talking about. That is, you that a classifier gives your output of 100% accurate on the training data but only 50% on the test data, when in fact it could have output that one that is 75% accurate on both. It has overfitting. So till your data is performing well on your test data, you can't say that your model is performing good, because suppose you have given your model some training data to test on only, is it is possible to give 100% results. Just imagine I have given you three questions and I told you the sum of the scores, the answer of these three questions. I told you that 2 plus 2 equals to 4, 3 plus 3 equals to 6, and 9 and 4 plus 4 equals to 8. And now if I ask you that what is 5 plus 5, then maybe you are not able to answer that, but you are able to answer 2 plus 2 equals to 4, 3 plus 3 equals to 6, and 4 plus 4 equals to 8. That is where overfitting comes into play. You are just memorizing the data, not learning the features from it, that plus is something that exists there. Hence you can see here that one way to understand overfitting is by decomposing generalization error into bias and variance. Bias is a learner's tendency to consistently learn the same wrong thing. Yeah, this is a very important thing, because this line I would refer you to write it down, is a learner's tendency to consistently learn the same wrong thing. Variance is the tendency to learn random things is irrespective of real signal. You are just randomly learning things that are not even required here to get the test data, test output nice. So a linear learner has high bias, because when the frontier between two classes is not hyperplane, the learner is unable to induce it. So you can even read that in detail here. I won't go in deep, because if I read every line it would take around 2 to 3 hours to read. Yeah, so you can see here what we do here. Cross validation can help us to combat overfitting, for example by using it to choose the best size of decision tree, but it is no panacea, since if we want to make too many parameters choices, it can itself start to overfit. So now I would talk about cross validation. Cross validation is a really important topic, because it's the only reason of the only method, not the only method, but a very widely used method of removing overfitting in our data. So yeah, coming to the next part, that is cross validation. Now we would be looking how cross validation and all its work. Basically I would just refresh this. And this is how cross validation works. You basically declare all the data sets and train on all groups but test on the last group for each possible combination. Here you can see there are 1 2 3 4 5 6 groups. You trained on this, you trained on this, you trained on this, or you trained on this, and you trained on this, but on this specific last group you basically tested on. So this is where you use this is where you use cross validation. Suppose you have 1000 data set data images. Now you split it into 200, 200, and just like that you split it 500 times. And after you have split it 500 times, what you basically do, you basically train it on 4 and test it on 5. As I have split it here, these are the 4 on which I would train on, and this is the one on which I would test on. So this is how cross validation would work. There is a lot of things specifically mentioned research paper on cross validation. If you want to study more about it, just search it and you can learn a lot more about cross validations. So now coming to an example, a mutual fund that beats the market 10 years in a row looks very impressive until you realize that if there are 1000 funds and each has a 50% chance of beating the market on any given year, it is quite likely that one will succeed all 10 times just by luck. So yeah, this is how all things work in machine learning. There is a chance that things get positive just because of luck, not because of the features, but because of the luck factor here. So this is a part of overfitting which we need to avoid, because overfitting is always really harmful for data sets and machine learning models. Now coming to the part, intuition fails in high dimensions. What is basically high dimensions? Okay, so coming to the part, this is the part. This is known as the curse of dimensionality. As this is said by Badri Shetty, yeah. As we add more dimension, we can also increase the processing power we need to train the model and make predictions, as well as the amount of training data required. As we add, let's read it once more so that we understand it. As we add more dimension, we can also increase the processing power we need to train the model and make prediction, as well as the amount of training data required. Every time, suppose this is a machine learning model that has 3 features. Okay. Now suppose the model is getting trained on these, and this is the power it's taking, and then it is getting the results. Now suppose I add one more feature. What would happen? Things would quite change differently. Yeah, so things would change differently. Now once we add one more feature, the power taken for the models to get trained and tested on would change, and the results would also change, because we need more data. Suppose you had 1000 images and that all images had 5 features. Now if you add more features, you need more images to get the data trained on them, because every time we test on, we would combine with permutation combination like this. These two would have, these two would have, these two would, and things change quite fastly here. Here you can see we need to increase the processing power to make the train the model and make prediction, as well as increase the training data required, because uh, yeah, to refer the fact that many algorithms that work fine in low dimension become interactable when the input is high dimensional, but in machine learning it refers to much more. Generalizing corrects between exponential header as the dimensionality of the example grows. So you can read it all here. I would just simply explain it in using an example. uh, you can see the performance of algorithm, the number, it depends on the number of dimensions, or you can see the classify performance is high at specific number of dimensions. It was not high here, it was not high, it was here, but as you increase the dimension, the number of features, it may decrease, but it is also has a chance. The performance on algorithms, the number of dimension, it depends on the number of dimensions actually needed for your model. We don't need all the features, we need the features that are really important for the predictions to be made, because definitely, as I show you in the dog example, we need color, but most importantly we need to know other features like eyes, ears, and nose, just like things like that. Now coming to the next part, that is what would happen if we add a new feature. Every time you add, suppose this feature didn't exist here, for now I would just remove this feature. Then just imagine all these things that are the convolutional network is following would have changed here. Just by adding this single layer, all things have increased gradually. You can see all the things here have increased gradually because of just adding a single new feature. You can imagine how big the model is going to change, how differently the model is now going to work after you just added a new feature here. Now coming to the part here, I would show you using TensorFlow and Keras how these all things work. The number of parameters in model 1 is 833. If we add just one more feature, not two, not three, not five, not any multiple features, just a single feature, it would increase to 1057. You can imagine how things change just by changing a single feature in the model from 833 to 833 to 1057. Things change so fastly because a single model can impact, so a single feature can impact so much on your model. So this is how all things work. I would just show you one more example. Here you can see two features combined together for one, and here you can see, yeah, and these together make prediction. Now suppose I add one more. You can just see how things change. Now this would be added to this, and this would be added to this, and all this would be working like simultaneously like that, and things change quite differently because you can see here the total number of parameters have changed from around 100, more than 200, actually almost 200, around 210, yeah, 225 parameters have been changed in this just because of adding a single more feature. This is how things fastly change in machine learning. As you can see here, for that it has even been said in the people could see in dimensions machine learning would not be necessary, but in higher dimension it is difficult to understand what is happening. This in turn makes it difficult to design a good classifier. Namely, one might think that gathering more features never hurts, since at worst they provide no information about the class, but in fact they may be outweighed by the curse of dimensionality. So this topic, that is curse of dimensionality, is a really important topic of how our things are going to work when you add even a single more feature into the whole production model. So now, yeah, you can see one of the code which I really love has been written here. One of the major developments of recent decades has been realization that we can have guarantees on the result of induction, particularly if we are willing to settle for probabilistic guarantees. So before coming to the part, just let's read this example. Fortunately, there is an effect that partially counteracts the curse, which might be called the blessing of non-uniformity. In most application, examples are not spread uniformly throughout the instance space, but are concentrated on near a lower dimensional manifold. For example, k nearest neighbors works quite well for handwritten digit recognition, even though images of digits have one dimensional per pixel, because the space of the digits images is much smaller than the space of all possible images. Learners can implicitly take advantage of this lowered effective dimensional or algorithm for explicitly reducing the dimensionality that can be used. It all depends even on the size of image, as the digit classifier size have, you can see, 1 pixel each. Hence things can be handled there, but every time you increase the dimensional, the pixel quality, the pixel size, the image size, things can act quite differently. 1 pixel for, you can imagine, 1 pixel for 1000 data images is different than 5 pixel for 1000 data images. Things would be quite different here than this. Hence this is how the curse of dimensionality works and how we can reduce it. We would talk about that, but before, just let's talk about one of the small topic, that is here. Theoretically guarantees are not what they seem. Machine learning papers are full of theoretical guarantees. The most common type is a bound on the number of examples needed to ensure good generalization. What should you make of these guarantees? First of all, it is remarkable that they are even possible. Induction is traditionally contrasted with deduction. In deduction, you can guarantee that the conclusions are correct. In induction, all bets are off. Or you can just read it, and it's not a very hard to read, you know. Unfortunately, guarantees of these type have to be taken with a large grain of salt. So these are, it talks about all the guarantees that are made in machine learning with the that this is the probabilistic thing that would occur, but this is all hypothesis about. For example, if there is a boolean 100 boolean features and the hypothesis based decision tree with up to 10 levels, to guarantee is equals to 1% in the bound above, we need half a million example, but in practice a small fraction of this surfaces for accurate learning. So this is how guarantees and all work here. Oh, I really personally love this thing that a dumb algorithm with lots and lots of data beats one a clever one with modest amount of it. Yeah, we would talk about it. But before we talk about it, let's talk about. We talked about cursor dimensionality, but we didn't talk about how to counter attack it, how to make sure that it doesn't occur with our data. So before that, here comes feature engineering. So featuring engineering is the key. So I guess I just wrote it here. Yeah, I guess, yeah. So I would just share up the PPT that I have created, specifically the images I have got for the research paper of this images. Yeah. So the feature, yeah, you can see here the feature engineering part. We need to manually create crafting features, certainly provide food for thought. We need to use engineering feature, that is aggregate, combine, decompose, extract context indicator, prescribe filters for relevant structures for images, come up with ideas to construct better features, diverse, devising features to reduce dimensionality, select the right features to maximize predictiveness, evaluate models using chosen features. Okay, now coming to here. Suppose we have got one, two, three, 4 and 5 features here. Now which features to use? Now suppose this feature is totally completely useless. It's just going to affect our model either in no way or either in a negative way. We know that okay, this feature has not got some relevant information even for predictiveness. What we would do, simply remove this feature from the model. Don't let it be the reason for the negativity in the model. Now coming to this feature, suppose this feature has got some abnormal results. Now what are abnormal results? Results which you don't usually predict, the corner cases or the cases which you usually don't expect the user to be part of. They are called the exceptional cases, or really cases like like the cases were going on 1 2 and suddenly it jumped to 1000. So this is how not things work here. You can remove that feature here. Yeah. And now we come to third feature. You see there are some this data is incomplete. There are 1000 tabular forms of data lines in this, and only 700 got responses which are accurate and correct to that, and the rest 300 are incorrect or are left blank. You simply remove this. You just test your data, train the model on the basis of these two features, and I guarantee you would get much better results than the previous data sets which you had, which had some irrelevant information and that wasn't required at all. So yeah, I guess, yeah. So reading some part here. At the end of the day, some machine learning projects succeed and some fail. What makes the difference? Easily the most important factor is the feature, because feature is the most important thing on which your model learns on. It decides that whether your model is going to look at this particular feature of, let's imagine dogs here. Dogs are our best friends, so let's talk about them. We don't need to make a choice here that okay, that a model should look at some features about dogs, that the dogs who have got eyes or don't have eyes. We simply have to look at the images which have the dogs have eyes, the dogs have got ears, and dogs have got tongue, and features some which are relevant to you. Now suppose you have got some features that okay, this dog is of red color, this is of black, this is of gray, and you're training a model on the basis of colors. I think that's not a good way to train a model. You should train your model on the basis of features which are really relevant to the model and increase your predictiveness in a positive manner. You can even use some TensorFlow libraries and Keras libraries for increasing the predictiveness of a model by using feature engineering. What is feature engineering? I just told you. You basically just I would show it once again. Yeah. As you can see, we need for manually crafting features. We need to look at each and every feature and look at how it's working on. Certainly, and for engineering features, suppose there is some tabular data, we need to aggregate, combine and decompose the data which is actually needed and which is actually not. Need to extract context and indicators. Suppose there are some positive text and you need our model to use some machine learning model to predict natural learning processing. At that time, how a model is going to do, it's going to extract. So as we already know about feature engineering, now we would be starting off with the last page and the last some rest of the part of the research paper, that is more clever data beats a clever algorithm. So basically in this I would just show you, yeah, it's a really nice thing said by Peter Novick, that more data clever beats clever algorithms, but better data beats more data. So yeah, whenever you are working with, I would again refresh this. I don't know why it's happening again and again today. So whenever you work on a specific model, what you need, as I told you, feature engineering using, you need good data. Suppose you have a lot of data available with you, but it is totally useless if most of that data is not a good data. Now, defining a good data depends on model to model, but here if you have got around 1000 images or 1000 let's say MB of data, and it has got around 60% of data which is not labeled properly, or is incomplete, and then you have 500 MB of data, and then if inside this 90% of your data is good, then according to me choosing this one is a better option, because now you have got 90% good data here. So more data beats clever algorithm, but better data beats more data. Same happens here. Suppose you have constructed the best set of features you can, but the classifiers you receive are not accurate enough. What can you do now? There are two main choices: design a better learning algorithm or gather more data. So yeah, so using that situation only, suppose I have the similar situation. I have built a classifier that difference between cats and dogs. Okay, I would just use something else here, which is differences between cats and dogs. This is cats and this is dogs. Now if my classifier isn't performing well, what my first approach should be? My first approach shouldn't be to look at the classifier, but my first approach should be collect more data, collecting more images of cat, collecting more images of dogs, to make the classifier work more accurately. And after that, even that doesn't work, then I would look at the model. Same happens here. Machine learning researchers are mainly concerned with the former, but pragmatically, the quickest path to success is often to get more data. As a rule of thumb, a dumb algorithm with lots of data beats a clever one with modest amount of it. After all, machine learning is all about letting data do the heavy lifting. So yeah, machine learning is all about how you can make the data more good, more accessible, and more accurate for the features, regarding the features for your machine learning algorithm and model. In the 1980s, it tended to be data. Today, it is often time. Enormous amounts of data available, but there is not enough time. Yeah, so there is a lot of data available for us there, but for processing it, we need good algorithms. We want data to get as soon as to get as predictive as it can be. So it is full of features, and for that, we also want a machine learning model to be fast, and because we don't have time. Suppose you have been given a deadline for production, you can't rely on fully on data. You need a good machine learning model which can perform your tasks at time, so it need to be fast. And except fast, what your model should be predicting data on the basis of the training data you have used, and for that data should also be good. So two things to keep in mind: data and algorithm. Yeah, obviously algorithm is for time complexity, and data is definitely for your, you can say, a type of accuracy. Yeah, so part of the reason is using cleverer algorithms has a smaller payoff than you might expect, is to first approximation and do the same. So yeah, you are using a really nice algorithm, it is fast and it really does things nicely than the algorithms which were performing on late timings. Learnings can be divided to two major types: those who representation has a fixed size, like linear classifier, and those who again grow with data, like decision trees. Yeah, so as linear classifier, You would train it and it would perform on the data which you have given the fixed amount, but the decision tree, it keeps on learning, keeps on performing. So it's totally a choice on how you want to use the feature engineering along with the algorithms, model algorithm status. So coming to the last part, I don't want this video to be so much big that no one even watches it. So learn many models, not just one. In the early days of machine learning, everyone had a favorite learner together with some prior reasons to believe in its superiority. Most efforts went into trying many variations of it, selecting the best one, then systematically empirical comparison show that the best learner varies from application to application. So why you should learn a lot of, not a single model. Suppose my model really worked nice on cats versus dog, it doesn't mean my model is also going to work on horse versus humans. 100% it's not. You should keep learning a lot of, a lot of models. You should keep learning things. You should not rely on a single model for everything, because data changes, features changes, variations are there, and you know one model can't perform good on every task. Okay, creating so what is, yeah, effort now went into trying many variations of many learners and still selecting just the best one. But then researchers noticed that instead of selecting the best variation found, we combine many variations. The result are better, often much better, and a little extra effort for the user. Yeah, so suppose I have a model. Yeah, okay, I have a model X and I have a model Y. I would choose this color X. Okay, this is really, yeah, X and Y. So now both the models are giving me some, like this is giving me 71 and this is giving me 74, let me say. But I want to increase the efficiency for both, for it. What can I do here? Either I can choose a third algorithm Z and say okay, it's performing good, or one thing I can do, I can add, we can combine both the algorithms and do some algorithm like XY here, which is giving me an accuracy of 89. Don't you think it's much better than this 85? Means according to me, I would just go for the algorithms I've already worked with and combining them, because it's all about collaborations of algorithms, you can say. So yeah, in the simplest technique called bagging, we simply generate random variations of training set by resampling learner classifier on each and combine the results by voting. This works because it greatly reduces variance while only slightly increasing bias. In boosting training, examples have weights, and these are varied so that each new classifier focuses on the examples the previous ones tended to get wrong. In stacking, the outputs of individual classifiers become the outputs of a higher level learner. You can learn this from a netflixprice.com, where there were a lot of models, a lot of algorithms that machine learner that Netflix wanted a hackathon to be part of, generating many. So you can see that in the Netflix prize, teams from all over the world competed to build the best video recommender system. As competition progressed, team found that they obtained the best results by combining their learners with other teams and merged into larger and larger teams. The winner and runner were both assembles of over 100 learners, and combining two assembles further improved the results. Doubtless we would see even the larger ones in the future. So yeah, you combine models, you get better results. It's always about how you can do some addition up in the machine learning. It would really help you up, and then you can read about simplicity does not. I would just link it. I won't be now telling you all this because it would make the video more long. But yeah, one more thing I would do, yeah, you can see here this was model B, this was model 1, this was model 2, and after we combine this, we get really nice results. It was here this, it was here this, but here it's really not bad, it's really nice. It's here you can see we combine three models to make a single model Y, and this is how you combine models to make it even better and make the understanding better by just by using this Netflix price competition tasks. So this was it for the video. I guess I should end up wrap it up. Today we talked about this really awesome deep learning paper by Pedro Domingos, and its name is A Few Useful Things to Know About Machine Learning. I would be linking it if you want to read it in detail. Go ahead, but I hope I have covered the major points that were really crucial part of machine learning, and everyone should know about them, because every machine learning beginner would like to know these points like feature engineering, over what is overfitting, how to overcome overfitting, how does machine learning and all its work, fairness in machine learning, and the theoretical guarantees, and in the high dimensional curse of dimensionality. It's one of my favorite topics I want to study about. It's like a complete theory part, and things keep going on like that. I hope you liked the video, and do give it a thumbs up if you liked it, because it is around, I guess, 35 to 40 minutes video. It took me long to study it, around 1 week. So thank you and have a nice day.